Okay, today's lesson is called Functions Defined by Integrals. This is our last new lesson of this unit, and so you also will be getting ready here to do the review and take your test over this information we've learned recently on integration. So, let's get started. We have 4 example problems to work with. This introduction here says functions defined by integrals overview. The definite integral of f of x on the interval from a to b is a number. Geometrically, that number can be interpreted as an area. Thus, we deal with something like f of x equals the integral from 1 to x of f of t dt using the ideas of area and the properties of definite integrals. It says capital F of x equals the integral from 1 to x of f of t dt is an integral starting at the lower limit of x equals 1. So f of 3, for example, would be the integral from 1 to 3 of f of t dt, which is equal to 6. So let me show you how they get that. If I am going from 1 to 3 for my x's, then the area between the curve and the x-axis would be this region here, and that's 2 times 3, which is 6, and they gave us that. Okay, so the easiest integral to determine is always going to be the one where the upper limit and lower limit are the same. So since our lower limit is 1 for this one, if we do the integral from 1 to 1 of f of t dt, that one will be 0. Okay, so now let's talk about some of these others. What about the integral from 1 to 2 of f of t dt? That means from 1 over here to 2. What is that area? Well, that's a rectangle, base of 1, height of 3, so that's 3. And let's see, going further to the right, what if we go all the way to 4? The integral from 1 to 4 of f of t dt would be what we had for from 1 to 3 plus this little trapezoid region here on the end. And this point, you can come up with a linear equation for this line to determine for sure what it is, but I'm sure that you calculus students can handle that, so I'm going to go ahead and tell you it's 4, 1.5. Oops, if you can read that. So using your good old geometry skills, you can find the area of this trapezoid and add it on to the 6 that we already had, and you will come up with 8.25, or 8 1/4. And if you just keep on moving along to the 5, you add on this tiny little space, which is an awkward shape and might be easier actually to just take your integral from 1 to 3. Let me erase this. Which was 6. And add on this triangle, which has a base of 2 and a height of 3. So that's 2 times 3 is 6, divided by 2 is 3. If you add that area of 3 to the area of 6, this one gives you 9 for the integral from 1 to 5 of f of t dt. Now, when you go, further along, this bit below is going to be negative area. And if you notice, this region from 5 to 6 is symmetrical with this region from 4 to 5. So that basically takes off the area that we just added on. So that brings us back to 8.25. And also, if you notice, this region here is symmetrical with this region here. So this takes off what we added on from 3 to 5. So that brings us back to 6. Okay, so we've gone through all these that are beyond 1. Now what about going backwards? Try to clear off some room here for me to work with. So what about the integral from 1 as my lower limit, 0 as my upper limit of f of t dt? That's going to be the same thing as the opposite of the integral from 0 to 1 f of t dt. So keep in mind we want our smaller number on the bottom, but that changes the sign of our area. So when I go from 1 to 0, I'm actually going to take the area from 0 to 1, which is this rectangle. Oops, I went a little high there. And that is a base of 1 and a height of 3, so that's 3. And change the sign on it to a negative 3. Okay. So, same thing for the negative one. Integral from 1 to negative 1 of f of t dt is equal to the opposite of the integral from negative 1 to positive 1 of f of t dt. So, if I look at this region from negative 1 to positive 1, it has an area of 6, and I'm changing the sign on it, so it's going to be negative 6. So now I've got my table all completed. Now, on these problems, sometimes they ask you to make a table, and other times they don't. Generally speaking, on these problems, I think it is easier if you start with a table, even if you're not required to best answer questions that follow. So, hopefully that gives you a good introduction of how we calculate these functions defined by integrals. Let's look at this example 1. Let f of x equal the integral from 0 to x of f of t dt. So this time our lower limit is 0. Complete the table. Then we're going to determine where is this function increasing, where is it decreasing, where does it have its maximum, where does it have its minimum, and sketch a graph. Okay, so you might want to pause the video and try to come up with these areas for the table on your own or with a partner, and then check to see if you got them right. The 0 to 0, of course, is going to be your easiest one. Top and bottom numbers are the same, then that just comes out to 0. From 0 to 1 is a trapezoid right here. And you can calculate the area of that trapezoid. It is equal to negative 2. Why is it negative 2 and not positive 2? It's below the x-axis. Now, when you go over here to positive 2, the symmetry here, you've got this much negative, then you've got this much positive. Those are the same, so it's actually, again, negative 2. At 3, we have this trapezoid here, which is the same as the trapezoid we started with, which balances out that negative 2 with a positive 2, so that gets us to 0. At 4, we add on these 3 rectangles, so at squares, the units, we have an area of 3. At 5, we're adding on 3 more, So we have an area of 6. We add on a triangle that has an area of 1.5 from 5 to 6. So that gives us a total of 7.5. Then we go back and subtract that same size triangle off from 6 to 7. The 1.5 comes off, so we're back to 6. At 8, we add another trapezoid on with an area of -2, so that gives us a total of 4. At 9, we have the same thing going on that we had back here with the triangles, a small triangle here and a small triangle here that have the same area. So we lose and gain the same amount of area, so we're still at 4. And then at 10, we're adding on this last trapezoid, area 2, which gives us a total of 6. Now, if you wanted to, you could skip B and C and go on to D to sketch the graph. Some of you are more visual. You might want to plot these points on the graph to kind of get an idea what's going on here. And, tables and graphs are good pieces of information. You may not need that though. But if you plot these, keep in mind, even though at 1 and 2 we're both at -2, this should not be a straight line from here to here, because the area actually does decrease and then increase again back to that same spot with the triangle thing we have going on here. We get a little bit more negative area, then we add positive area. Those balance out to get us back to the same place. 3, we're at 0. 4, we're at 3. 5, we're at 6. 6, we're at 7.5. 7, we're at 6. 8, we're at 4. 9, we're at 4 again. That's this little triangle area. It actually does decrease a little bit, then increase back with that balancing out of the triangles. 10, we are up at 6, and that's the end of our story here. So, on what subintervals is f increasing? Well, the area is increasing from okay, I'm sorry if the video is maybe not very smooth right here. I had to pause it, and then when I came back after recording some more, I realized that I hadn't actually been recording, and so anyways, it may not be just perfectly in sync, but I think I've got it close. So I'm going to start working now on number 2, part B. Determine the x values where the relative extrema of f of x occur. Relative extrema are maximums or minimums. Those are going to occur when the first derivative changes signs, positive to negative or negative to positive. So we've just determined in part A that the derivative of f of x, capital F of x, is lowercase f of x, which is what this graph here shown represents. So, we're looking at where does it change signs. It only changes signs from positive to negative one time at x equals 3. So our justification, we're going to say, since it is going from positive to negative, that's a maximum. Positive to negative makes a maximum. So we're going to say is a max because f of x changes from positive to negative. Okay, for part C, I would suggest that you push pause on your playing of this video and complete the table on your own. Then you can turn the video back on to check your answers. We here are finding the integral from -1 to x. So for example, -1 to -1 of f of x, or f of t dt, is 0. Then from -1 to 0 would be the area of this region, which is 1.5. Then we add on the area of this region to get 4. Then we add on this region to get 7. And then we add on this triangular region here to get 8.5. And then we come back and subtract out that same amount, because it's negative now, to get 7 again. And then we add on this portion, which gives us -3 from 7 is 4. And then we have another -3 for this rectangular region, which gives us 1. So D says, what is the maximum value of f of x in the table? That would be 8.5. Does this agree with your answer in part B? Part B said that x equals 3 was the maximum, and at x equals 3 is where the 8.5 occurs. So yes, it does agree with that answer from part B. E says, determine the x values on the open interval from -1 to 6, where f of x is concave down, and explain your reasoning. Okay, so concavity is by the second derivative. Now the first derivative of capital F of x was lowercase f of x, which was just looking at the values graphed in this picture. But the second derivative would be f prime of x, which means we're looking at the slope of the graph shown. So we're looking at where is the slope negative. So we're going to say f prime of x is the second derivative of capital F of x, and f prime of x is less than 0 on the interval from, where is my slope negative? Well, it's positive, constant, then it goes negative here, then it's constant again. So that's from 2 to 4. So I'm going to put 2, 4. And that takes care of that one. Alright. This is our last example over this section. F is the differentiable function whose graph is shown in the figure. The position at time t seconds of a particle moving along a coordinate axis is the integral from 0 to t of f of x dx. So we have a function defined by an integral. Use the graph to answer the questions, give reasons for your answers, and here we have units or meters. A. What is the particle's velocity at time t equals 5? Okay, we're looking at velocity. Now this integral represents position. So the velocity would equal the derivative of the position function. Which is f of t. So we're just going to say f of 5 equals, and I'm going to come over here to my graph, f of 5. This f of x graph we know is velocity. So when I see 5 for x, the y value that corresponds to that is listed there. It's 2. Alright, B. Is the acceleration of the particle at that time, t equals 5, positive or negative? Well, f prime of 5 is the slope of f of t at time equals 5. So is the slope positive here or negative here? It's negative. Okay. Part C. And you can see that because this graph is decreasing here. Part C. What is the particle's position at the time t equals 3? Well, that's going to be the position function, the integral from 0 to 3 of f of x, f of x dx. Okay? So that's going to be the area between the curve and the x-axis from 0 to 3. So that's this region. It's a triangle, base of 3, height of 3. So that's base times height divided by 2. 9 divided by 2 is 4.5. Let's see, I guess I should put some units on here. Meters. And the velocity up here on part A should have been meters per, what is the time measured in? Seconds? Okay. Now, last part D. At what time during the first 9 seconds does S have its largest value? Okay, keep in mind, S means position. So when is my position the biggest? Well, the position is represented by this integral. So I'm looking at when have I accumulated the most area under the curve, the most positive area under the curve. So I'm getting positive area everywhere from 0 to 6. Then I start subtracting area off. So my largest position is going to be at the time t equals 6 because I've accumulated the most positive area at that time, and after that I begin losing area. 6 seconds. Okay, well, that's all for functions defined by integrals. I wish you all the best with your lesson. Bye.